Thank you very much for giving me this opportunity to present this paper of mine here. Before I even get started, I would like to congratulate the team here for their successful 50th edition of this conference. I have known Professor Todorovic for a very long time, and to be able to be here my second time in Serbia at this conference, it is indeed a pleasure for me, and I'm absolutely delighted to be part of this meeting here this week. And again, I would like to thank Professor Todorovic and the team for inviting me here to make a presentation. And I've been sitting here listening to all the talks earlier, and just realized that what you're going to be hearing from me is somewhat different, not entirely, but certainly I'm not going to be talking about refrigeration system or refrigerants per se. Can I get the slideshow on? Oh, it is, okay. So I'm not going to be talking about the refrigerants or refrigeration systems per se, but certainly when we are looking at it in terms of what the relevance is, it's really for what we need in terms of environmental control in buildings. So I'm on the air conditioning part and related to buildings and the built environment. So we know that buildings and the built environment are a very important part of what we do in life, and it's no surprise that we spend more than 90% of our time in built environments. So obviously it is very important in the context of what we do and what we need the environmental conditions for. So this particular presentation, I looked at it from the point of view of how does a HVAC system impact whatever we do in the buildings in terms of the user needs, whether it is for the comfort air conditioning, primarily for comfort air conditioning in what I'm going to be talking about. So let's just see. The role of HVAC system is for indoor environmental quality, that's comfort and indoor air quality and those sort of things. And of course the energy efficiency side of things. So we can't be using energy indiscriminately in that sense, and we have to keep that in mind and also ensure that the user needs are not compromised in any way. I titled this paper calling it the tropical low-hanging fruits. Tropics because I come from Singapore, and I don't know too much about heating. Of course, I know the science and the engineering side of things. We don't do that in Singapore. We don't need that. The lowest temperature we ever get down to is about 21 degrees Celsius at any time of the year. And it's extremely hot and humid, so my focus would be, what do you do when the environment outside gets 35 degrees Celsius and you step out for a moment, you are drenched in sweat? That's what happens to me. And by the way, I've been living in Europe for the last 5 months, and I don't think I sweated much at all. So here it is, the tropical low-hanging fruits. Simple, innovative, cost-effective sort of solutions that we can think about that we can implement in any building. Of course, for newer buildings it becomes easier, but can we do that in most buildings that we are normally talking about? So I'm going to run down through a series of what I call strategies or technologies. Again, something that we've been working over a long time. I'm a professor in the university, and I've probably spent most of all my career in this field, in thermal comfort, indoor air quality, and HVAC systems. So there's nothing here that's an outcome of a particular study, but a series of techniques and strategies that we have explored in the past, focus being hot and humid climate. So here it is, high temperature cooling and dehumidification. Interesting observations that we are ourselves beginning to see. Humidity level inside the building above a certain value, say 80% relative humidity, has tremendous impact in terms of how we perceive and how it affects us. But anything in the range of about 60, even 65% relative humidity, you've got better means of providing comfort. So the question here is, do you really need to dehumidify down to a very, very low dew point temperature? And it turns out that we may not need to do that all the time. So the question here is, can we do high temperature cooling and dehumidification? Conventionally, consultants design systems for something like, say, 7 degrees delta T between chill water supply and chill water return temperature, chill water supply being at 6 to 7 degrees. And you're talking about what would happen if we increase the chill water supply temperature to 10 degrees? the benefit in terms of chiller energy performance is very obvious, and that's really what I'm alluding to here. And it doesn't really compromise, it wouldn't really compromise that significantly. In fact, there's probably no impact in terms of the humidity level inside the building, because if the levels do rise, which it will, we can probably accomplish comfort in a slightly different way. And I'll come to that as part of another strategy as we go along. The next one that I would like to just very briefly mention this to you here is what we call an adaptable coil approach. Conventional cooling coils in an air handling unit, let's say we're talking about a 6-row deep cooling coil that gets, say, chill water supply temperature, what I told you earlier, 6 to 7 degrees Celsius with a delta T of similar number, 7 degrees delta T. And you have your environmental conditions in the room, typically being achieved at 23 degrees Celsius and about 50% RH. Now, when I say this typical, I say this because that's what the designers do. What happens in operation is you end up operating that same cooling coil, which is oversized, in such a way that at part loads, it tends to overcool the space. So it is not uncommon, even in today's context, in a lot of tropical buildings, that you enter the building and you feel cold. I mentioned earlier we don't have winter in Singapore and in that part of the world, but if you want to experience winter, I can take you to some buildings and you would experience winter. 21 degrees Celsius, 19 degrees Celsius, people wearing light jackets, sometimes maybe heavy jacket. Can you imagine 35 degrees Celsius outside and you're wearing jacket inside? That's not what we should be designing buildings for. So what we're talking about here is if you had to build in capacity and the cooling coil is oversized, how do you make that work in real time, in the dynamic operation of the building, to make sure that it can adapt itself to a smaller capacity, which for a variety of reasons, for good dehumidifying performance, you would want to reconfigure the shape and the size and the geometry of the coil. So what we are really doing here is we just change the 6-row deep coil into effectively a 3-row deep coil by manipulating the chill water circuits so that you end up having smaller surface area of the heat transfer. Thereby you can get your required, shall we say, the coolant velocity, the chill water coolant velocity, in a way that optimizes the interface temperature. Let's bear in mind that if you want to achieve good dehumidifying performance, you would need to have the surface temperature as cold as possible. And that's what this particular strategy does. You design, you probably over-design, no issue with that. When you operate it, you can effectively kind of fine-tune the operating point to get that sweet point of operating conditions that matches your required effective surface area with what is actually happening in the buildings. Now, I'm just presenting what we've been doing over years in just a 2-minute discussion with you, but we can discuss later with, if you have interest in an offline session. So we call this adaptable coils because it adapts itself in dynamic operation of the building. Heat pipes, I'm sure most of us here in the audience will be familiar with what heat pipe is. And again, for us, heat pipe as a passive energy recovery feature, passive technology, is beneficial if we can implement that in an air handling unit where you want to control both the dew point. Let's not forget that the design consideration has always been, let's address dehumidification needs in an effective, energy efficient manner. So I would not want to just trivialize the need to have good humidity control. We need that. In certain applications, you do need to have a fairly dry condition. So heat pipes really help in that sense. Let's see how it works. We got a cooling coil that's in operation, and we just wrap around a heat pipe around the cooling coil. So this is your evaporator section, this is the condenser section. So pre-cooling session and pre-reheating section. So what happens is the hot and humid air, as it goes through this heat pipe, it loses its heat, delta T, temperature drops, and the heat is then transferred to the downstream of the cooling coil. So you pass the heat required from the hot air to an overcooled air, so you don't have to spend energy, reheating energy in terms of correcting the sensible temperature. Now we did some studies about this. We did some studies in this in an animal care facility as I've written here, and we were able to through measurements, document about 18% energy saving, which is quite significant, especially when you're talking about 100% or dedicated outdoor air system. A fourth strategy that I'm talking about here is elevated space temperature at elevated speeds. What does this mean? Thermal comfort. Let's go back to basics. What's thermal comfort all about? These are the parameters that we are talking about. There are some physical parameters. There are air temperature, drivable temperature, radiant temperature, relative humidity, and airspeed. Now what happens is, we usually use the air temperature. Cool, cool, let it be cold. Wear a jacket, no problem. Get your comfort. What we are now trying to say is, there are other ways in which comfort can be achieved. This has been the conventional approach. So why can't we make use of this factor, the airspeed, to provide that, that effect of cooling that you can achieve by simple strategy? What did our forefathers do? If you feel hot, just take a sheet of paper or leaf, just fan yourself. Airspeed works tremendously, and that's what we are trying to accomplish here. How can we build that as part of our design strategy, a design concept for tropical conditions where you can get your comfort by not having to use active, say, vapor compression system type of an energy that's going to increase our energy budget and really not be the most effective way of doing things. So here, when we look at this, for what we have applied in one of our latest buildings that's come on campus in our own school, it's the net zero energy building that just got commissioned early this year, to be precise. Some of my colleagues and I were involved in that. The idea is conventional design, 24 degrees indoor temperature, and you have cold air being supplied, out of the normal cool air being supplied. That's the only way you get your comfort. If you raise that temperature to 27 degrees, leave everything else the same, it's not quite comfortable because 27 degrees and normal 0.1 meters per second or below of air movement doesn't really give you a pleasant sensation. But if you augment that with a ceiling fan or a table fan or whatever, you know, air moving device that you can think about, it's tremendous. The advantages are tremendous, and you obviously save a lot of energy, no doubt, and it provides that comfort and the pleasant sensation that occupants experience in the buildings. So this is the latest building that I was talking to you about, the first net zero energy building, purpose-built, designed and purpose-built in Singapore. One other strategy, move less air through the HVAC system. I'm sure this is something you all relate to. If we don't have to move as much air through the building, then obviously we save energy, the air transport energy. So in this context, we've done some desktop study or simulation study where we find that if you change the delta T of the space, that means 5 degrees C has a lot of air to be moved, as compared to, say, 8 degrees C, you're talking about a factor of 2.2 in terms of the air transport energy. We can avoid that if we can reduce the amount of air that needs to be moved through ductwork and that sort of a thing. So this then leads to what, okay. So this is the one that is related to the earlier strategy of not having to move too much air. That means if we can decouple ventilation from cooling, in other words, your indoor air quality needs from thermal comfort needs. That's better. That's tremendous benefits in terms of how you can manage each one. And here, the concept of dedicated outdoor air system is the one that I'm trying to sort of focus on. With the outdoor air for ventilation and indoor air quality being on a separate system by itself, we can accomplish our thermal comfort needs in more ways than one. The conventional strategy has been we just move recirculated air, mixing with outdoor air, whatever, and that's a lot of air being moved, not the most optimal way of doing things. So we are now talking about, can we decouple it, move only the ventilation air, which we don't have any other way of accomplishing that, that requirement. Outdoor air, whether it's for heating or cooling, we need to take it from outside, filter it, cool and dehumidify, or heat it and humidify if needed, then provide inside for ventilation. But for heating, here in this part of the world, you have tremendous systems of radiant cooling or radiant heating, radiant panel heaters, and other ways of accomplishing it. For the tropics, to accomplish radiant cooling or any other means of cooling is something that's beginning to get our attention. The only problem with that sort of a strategy in the tropical world is if we use radiant cooling, as the one I'm showing you, chill beams is one strategy that has been working quite, beginning to be seen to work quite effectively. Although there are some considerations, I'll come to the consideration just in a minute when I go to the next slide, which is about the chilled ceiling or radiant cooling panels. Our concern will always be issues related to condensation. If there's infiltration from outside, the hot and humid air will come into the building, and this can pose a lot of other problems, mold related and that sort of a thing, that consultants usually tend not to go for chill ceiling or radiant cooling sort of a design concept. Although we are now arguing from an energy efficiency point of view, buildings are being designed and built airtight, so you can manage the extent of infiltration, if any, that would occur. So this could be a fairly viable strategy moving forward in terms of tropical designs. Okay. Seventh strategy or seventh approach that we could think about. Look at the amount of humidity that gets condensed on cooling surfaces in an air handling unit. So the idea here is, can we recover any cooling effect from the condensate that's collected that otherwise would just go down the drain, and get something as a passive or energy feature from the whole process. So this is a study that we did some time back, and here the concept, you can see there are 5 air handling units treating outside air. We collect the condensate from that into a 6th air handling unit. So let me just focus for the 6th unit here. So what we try to accomplish is, can we get some cooling out of that condensate? And sure enough, we were able to get about 9 to 11% of pre-cooling energy savings, and the fact that the condensate eventually is still cool enough to be able to be replenished as cooling tower water. So there's energy recovery, there's water recovery, and this is something that, if we can focus on how it can be better implemented in buildings, has the potential to give us a lot of mileage in terms of what we want to do. Nothing new, nothing fancy about it. It's just the way the design can be concretized and implemented in buildings. 8th strategy, UVGI, ultraviolet germicidal irradiation of cooling coils, the heat exchange surfaces. All of us know that cooling coils can get quite contaminated with a lot of biofilm and other dust particles accumulating on it. Placing a UVGI downstream of the cooling coil shines the coil surface with the UV radiation, keeps the biofilm out of contact and formation. Basically, it keeps the coils clean. There are 2 benefits. It keeps the coil clean. It also allows us to disinfect the air in terms of killing all the microorganisms or biological contaminants. So we did a research project, and here you can see the semblance of what that is all about. Keep the coil surface clean, you get energy benefits, you also get indoor air quality benefits. So I'm just showing 2 of those measurements and what we got out of it. If you look at the left-hand, or your left-hand side chart, the thermal conductance, you can very easily see the benefit that we get after UVGI irradiation, because we did this as a protocol, monitored for 2 months before UV turn on, and then monitored for 1 whole year after UV turn on in an actual building. So the benefit is very, very evident over there. And so is on this side over here, the increase in the heat transfer coefficient. It's very simple. If you keep the surfaces clean, the resistance is decreased, you have better heat transfer occurring on the surfaces, and that's exactly what we're talking about. So there it is, the benefit of the UVGI coils. Now I'm going to come to the conclusion of what I spoke to you about. And I thought about, how do you club all of this in the context of a HVAC design professional? I just thought, let's just call it simple strategies. Can we just put it into the system in place? So I'm just calling it low-hanging fruits. So what I spoke to you about is high temperature cooling and dehumidification, adaptable cooling coils that can change its effective surface area. Then I spoke to you about heat pipes and see how that can be beneficial in tropical designs, about 18% or so. Elevated space temperatures accompanied with elevated air speeds, that provides us an alternative way of achieving comfort rather than just usual cooling process that we are comfortable with. UVGI systems that keeps the coil surfaces clean and thereby enhances the heat transfer. It has both energy benefits and indoor air quality benefits. The condensate energy recovery, which again allows us to get some pre-cooling from the condensate as well as cooling tower water recovery benefits. Decoupling the ventilation and cooling systems, it's a strategy that's now beginning to be well received in tropical designs too. Let's not combine the two processes, comfort and ventilation. They're two different things in that sense. And people do respond differently. So we can achieve the two quite successfully if we decouple the two. And move less air through the HVAC system, thereby reducing the air transport energy. I'm just calling all of this tropical low-hanging fruits. Not exhaustive by any means, there could be more, but just my thoughts, and I thought of sharing that with you. Thank you for your attention. If there are any questions, I'll leave it to you for how you want to manage the process.